Let us do one more problem on two-port networks. The problem reads this way. We are supposed to find the y parameters of the given network. And secondly, what would be the y parameters of the resultant network if two such given networks are connected in parallel? So this problem has two parts. One is we're supposed to determine the y parameters of the given network. And then the second part would be to find out the y parameters of the resultant network if two such networks are connected in parallel. Let's go one by one. First part we will try to attempt. We will try to recollect what do we mean by y parameters, how are they connected. If we recall, y parameters are nothing but a relationship between the two-port parameters. That means relationship exists between the input port parameters, that is V1, I1 and V2, I2. Okay, these are the four parameters we have. The relationship that exists between these four variables would define various parameters. So y parameters are those parameters wherein our independent variables are V1 and V2 and dependent variables are I1 and I2. In other words, y parameters can be described by I1 and I2 as a function of V1 and V2. So V1 and V2 are independent variables and I1 and I2 are dependent variables. How are they related? If we recollect, we have this theoretical background. I presume that you have this theoretical background. I1 is y11 V1 plus y12 V2. The current in the second port, I2, is y21 V1 plus y22 V2. We need to pay attention here about the positive direction of flow of currents. So current into the port is taken as positive, right? So this has to be clearly understood. And now this is the problem we have before us. We are supposed to find out y11, y12, y21, y22. How can we determine these four parameters? It is simple, by either short circuiting the output port or short circuiting the input port. One at a time. If we short circuit the output port, we mean V2 is made 0. So obviously these two will go away. In that case, we will be able to determine y11 and y21. On the contrary, if we short circuit the input port, thereby making V1 0, we will be able to determine y12 and y22. So y parameters are also called short circuit parameters. Y parameters are also called as short circuit parameters. Because in order to determine these parameters, you need to short circuit the ports. So with this background, we will attempt this problem. We will try to see how this problem can be solved. If you look at the given network, this is a two-port network. Like I can have a black box enclosed this way. This is the network. Within the square we have the network, that is a network, and we have the two ports. A port is constituted by a pair of terminals, right? So 1 dash would constitute one port and 2 dash would constitute another port, right? So let us try to see the shape of this network. If we can identify this network as a pi network, and if we can identify these things as, let us say, YA, YB, and YC, we can easily determine y parameters. Okay, so all the values that are given are admittances, right? So they are the admittances, reciprocal of impedance, right? So we are supposed to determine the parameters. Okay, so how do we do? We will try to write the equations once. What is y11? So y11 can be determined by making V2 0 from equation 1. I'll call this 1. This is 2. From equation 1, if I make V2 0, then I1 to V1, this ratio, current to voltage ratio, with V2 equal to 0, is y11 from equation 1. Similarly, from equation 2 with v2 equal to 0, we will be able to determine y21. Okay, so y21 obviously is I22 v1. Current to voltage is admittance, but hence the name admittance parameters. So v2 equal to 0. Okay, so in order to determine the other two, we need to make v1 0. So what do we get? So y21 is I2 to v1. I'm sorry, we are supposed to determine y12, right? y12 is I1 to v2 ratio with v1 equal to 0. And y22 is I2 to v2 with v1 0. Okay, so this is how we determine all the 4 parameters. So one thing is clear, we need to short circuit either the output port, that is make v2 0, by which you will determine y11 and y21, and by making the input port shorted, by shorting the input port or making v1 0, we will be able to determine the other 2 y parameters, that is y12 and y22. Let us proceed now. For the convenience, I have named these admittances as YA, YB, YC, and we will see how we exactly get the parameters, right? So we will rewrite the network. I'll copy the network. I'll take this network. I'll copy this. I'll paste it here. Okay. Now, what I'll do is, I will now short circuit one of the ports. Okay. So what I do is 2 and 2 dash. This is 2 and 2 dash. We will try to short. I'll take this red color because red is pretty, indicative of short circuit. Okay, I've shorted the port. So what will happen when you place a short between 2 and 2 dash? So it's very clear that there is no voltage available here. So V2 becomes 0. Alright, so V2 becomes 0 is the situation. Okay, so the positive direction of flow of current is I2 is into the port. Now with V1 as the voltage to energize the circuit, how the current flow is going to be? The current would branch out into 2 parts. One current will flow via YA, the other current will go via YB, and it will pass through the short circuit and come back to 1 dash. So for all practical purposes, your YC, this branch of 1 ohm admittance, is open, like it doesn't have any role to play. It appears as though it is open, right? So there won't be any current. Now if I want to determine the ratio of I1 to V1, what is it I get? If I have to get I1 to V1, that ratio is the sum of the admittances, right? So YA and YB, they are appearing in parallel, right? So when they appear in parallel, the admittances are the sum, right? So I1 to V1, what is this I1 to V1? I1 to V1 we know is Y11, okay? This is at V2 equal to 0, right? So at V2 equal to 0, I1 to V1 ratio is simply YA plus YB. Okay, so if the admittances are in parallel, then the equivalent impedance is the sum of the two. This is something we know, right? Impedances in parallel would be the product divided by the sum, whereas admittances in parallel is equal to simply the sum of the two admittances. Alright, so we are able to find out Y11. So what is YA and YB? We will now substitute the values. This is 1 mho plus this is 2 mho. So their value is 3 mhos. Okay, so Y11 is 3 mhos. So we are able to determine one of the parameters. Okay, and now we will try to look at the other parameter. We will try to find out what is the relationship between y21. We will try to determine y21. What is y21? At the same condition, that is v2, with the same condition v2 equal to 0 or short circuiting the output port, I2 to V1 will give me y21. So it is proper to determine y21. It is easy to determine y21 right now at this situation. What is y21? So y21, I'll pick up my white color. y21 is essentially given by I2 to V1, right? So it is I2 to V1. This is something we know. But what is I2 in the present situation? What is the current? What is the current? So if I can look at this network, so the current would be I1 current would branch into YA and YB, right? So what in YB the current would be from this is the direction of flow of current. This is the direction of flow of current, right? So I2 is into the port. Actually the current flow is away from the port. The current would circulate like this, right? This is how the current comes, right? So I2 is actually flowing away from the port. So if I have to determine I2, what is I2 equal to? What is I2 equal to? If I determine I2, this is equal to, the current is flowing actually against the convention, hence it is minus, it is the voltage times the admittance. So voltage across YB is V1, V1 times the admittance is the current, okay? So I2 is V1 times YB. Why we have given a negative sign here? It is because it is flowing opposite to the conventional current. Conventional current is into the port, whereas actual current is flowing away from the port. So actual current is negative of the conventional current. So I2 is minus. How do you determine the magnitude of current? It is voltage times the admittance, because voltage divided by impedance is the current, voltage multiplied by admittance is the current, right? So if we can get the relationship, we will get our y21. Okay, so from this y21, what is y21? It is I2 to V1, right? You look at this expression, okay? So this is obtained at V2 equal to 0, okay? And this is equal to minus YB, and YB is 2 mhos. Okay, so we are able to determine the next parameter. That is y21 is minus 2 mhos. Okay, so we'll try to put it in a box so that we can collect them later, right? So this is another value. So we are able to determine 2 quantities. What are the 2 quantities we are able to determine? We were able to determine y11 and y21. This is possible with V2 being made 0. Okay, so y11 and y21 we have determined. So we are now left with the other 2. The other 2 parameters are y12 and y22. They can be determined by making the input voltage 0 or short circuiting the input port. Okay, so we will now try to do that. Okay, I will write here. This is short circuiting output port. Okay, now what we will do is we will short circuit the input port. What do we do for that? We will pick up the network. I'll copy the network again. Copy the network and paste it. Okay, now what do we do is we will try to short this port. we will try to short this port. Okay, so if we place short across YA, the voltage is 0 between 1 and 1 dash. Now V1 equal to 0. Okay, this is the voltage, V1 equal to 0. Okay, now how do we proceed? Now we will determine the other two quantities, right? So what is Y22? We know that Y22 is the ratio of I2 to V2 with V1 equal to 0, right? So we can easily see what is it. So if you look at this network, Y2 is the voltage available. So the current I2 will enter this point and it will split between YC and YB. The current which flows via YB will pass through the short circuit and come back to the supply. Or YB and YC, they are in parallel. These two admittances are in parallel, right? So if I have to write down what is Y22, Y22 is the ratio of I2 to V2 with V1 made 0 is simply the sum of these two, that is YB and YC, because YB and YC are appearing in parallel, right? So YB is 2 mhos and YC is 1. This is equal to 3 mhos. Or in other words, Y22 equal to 3 mhos. Okay, so we are able to determine one more parameter. Okay, now the fourth parameter that we need to determine is Y12, right? That is the thing that is left out. What is Y12? Y12 is I1 to V2 with V1 equal to 0. Okay, V1 we have made 0. So we have to find out what is the magnitude of I1, and I1 to V2 ratio we will have to find out, right? So what is I1 now? So I1 from the circuit diagram, if you look at the circuit diagram, this is where one has to be little careful. So I2 will split into two. One current will flow via this, the other current will flow via YB. Whatever current that flows via YB will flow out of the port via 1 dash, it will come back to the supply. Or the actual current is opposite to the conventional current. So what I mean is, the current that flows here, this is I1 only. Or this current is now actually opposite to what exactly is the conventional current. Rather, I would write the current at I1 that is going to flow. This is I1 now, actual current I1 is opposite to the conventional current, positive current. So I'll have to have a negative sign. What is the magnitude of this current? This is the voltage across YB, that is V2 times YB. Okay, so if we go ahead, now this is I2 to V2 with V1 0 is what we call as Y12, rather this is I1, this is I1 to V2 and this is Y12, and this is equal to minus YB, this is simply minus 2 mhos. Alright, so we have now Y12 parameter is minus 2 mhos. I use my yellow colored and I put. So we are able to determine all the 4 parameters of this particular network. So we will try to summarize the results. We will put the results in one place. So Y11 is found to be Y22. This is equal to 3 mhos. And Y12 equal to Y21, which is equal to minus 2 mhos. And this completes the problem, first part of the problem, wherein we have determined the Y parameters of the given network. Okay, find the Y parameters of the given network, right? The first part is completed. What is the second part? What would be the Y parameters of the resultant network if two such given networks are connected in parallel? So what it means is, we have this network, this given network is paralleled with an identical network, and what would be the y parameters of that. So we have a proof for this. When two networks are connected in parallel, then the resultant y parameter is the sum of the individual y parameters of the independent networks. That there's a proof. So maybe I'll give the proof in my next video, but then that result can be made use of. So we will first try to see if the part 2 of the problem, we will write part 2. Okay. So two such networks are connected in parallel. What is the appearance? How does it appear? How would the network appear? We can do it by different ways. Okay, we'll make use of the result, or we can simply write two networks are connected in parallel. How would it appear? How would it look? We can write it this way. I think it makes sense if we can write it this way. When the two of such networks are connected in parallel, it would have an appearance of this nature. I'll copy this part, paste it here, and paste one here, and I'll rotate this, plug it here. What I'm trying to do is, I'm just paralleling this network. I'm trying to compress this whole thing into a small unit. Okay, so what I have done is I have paralleled the two networks. So if I parallel, what I'll get is, I'll get a 2 more here. This is a 2 more. This again is my 2. This is 1. This is 1. This is 1, and this is 1. Alright, so this is my V2. This is I2. I'm taking the positive directions of flow of current, I1 and V1. Okay, this is my 1 and 1 dash terminal, which would make it an input port. A pair of terminals 2 and 2 dash would make it an output port. Right? So now this can be further written as, if we can see this network can be rewritten as equal to, the resultant would be like this. I have paralleled the two admittances. So what I get is, this is 4 modes, 2 and 2 admittances in parallel. 2 modes and 2 modes in parallel would make it 4. This is 1 and 1 parallel would make it 2. Again 1 and 1 parallel would make it 2. This is my 1 and 1 dash. This is my 2 and 2 dash. Okay, so now this is the resultant network. This is my figure 1. This is figure 2. Figure 2 is the resultant network of two given networks in parallel, right? So this is V1, this is V2, this is I1, this is I2. Okay, if this is a situation, how do we write the parameters? Y11 is simply the sum of the two. If we can name them. It is easy. You can name these admittances, and you can simply write it as it is a summation of YA and YB, but you should know which is YA and which is YB. Or otherwise also, simply if you can inspect the network, it becomes very simple. So Y11 is I1 to V1 with V2 0. This is equal to 4 plus 2, the same logic that we had earlier. This is 6 Mohs. Okay, then Y21 is minus of YB minus of this element, that is 4 ohms. So you can use it as a result. This is I2 to V1 with V2 0. This is minus 4 Mohs. Similarly, other two parameters, Y22 is I2 to V2 with V1 0. You can use them as straight results. You need not have to every time do the shorting the port and obtaining the results. Instead, you can simply write the values. Now this is I2 to V2 with V1 equal to 0. V1 equal to 0, then it would be the sum of these two things. This 2 and this 4, they are in parallel. So that would be 4 plus 2 again. 4 plus 2, that again is 6 Mohs. And Y12 is I1 to V2 with V1 0. This is minus 4 Mohs. So this is how the resultant values are. We did it by first principle. Y11 equal to Y22 is 6, and Y12 equal to Y21 equal to minus 4 Mohs. Okay, so we did this. Okay, this is the resultant. If two identical networks are connected in parallel, this would be the resultant Y parameters. This can be obtained by making use of another principle, that if when two networks are connected in parallel, then the Y parameters of the resultant network is the sum of the Y parameters of the individual networks. We can simply make use of that law also, and we can do. So what we did here right now is from the first principle, but still you can simply make use of this particular result. We know that when two networks need not be identical, when two networks are connected in parallel, then the resultant Y parameters of the resultant network is the sum of the Y parameters of the individual networks. Okay, so that means you have identical networks in this case. So this network, you have another network of the same nature, and you are paralleling the two. So the Y parameters of the resultant network is the sum of the Y parameters of the individual networks. So if we can make use of this result, this is the result we have. So we can make use of this result, and then we can deduce the same y parameters. That means if I can write y11 is simply, for the first network it is 3 Mohs, for the second network it is 3 Mohs, we have added the 2 and we get 6 Mohs. Similarly, y22, if we can see, it again is 3 plus 3, which is 6. y21 is minus 2, that is minus 4 Mohs. y12 is again minus 2 and minus 2, minus 4 Mohs. We have simply made use of this principle and we are able to get the y parameters. Right? So from the first principle we have got the same thing. This is our result 1. This is from first principle and this is our second. This is from this particular law that we have made use of. There is a proof for this. There is a proof that is, one can refer to the proof. There is a proof for this. One can look into the books and get the proof, or else I'll make a video for, to have as a proof of this particular statement. That I'll make another video. Alright, so this is how we determine. So one thing that is worth noting here in this problem is the given network is what we call as a pi network. Pi network. Let me be a little neat in writing this. This is pi network because it resembles this shape. Pi network, right? Pi network. So we have a resistor here, we have a resistor here, we have a resistor here. That means the shape is, if I can show you with the highlighting, this is one arm, this is another arm, the third arm. It is like pi, isn't it? So that way we make use of this particular. A pi network is useful. This shape is useful to determine the y parameters. So if a network is available to us, if we can convert it into this shape, the pi shape, it becomes easy to determine the y parameters. Similarly, for impedance parameters, T-shaped network is comfortable. So we know from star-delta connection, for star-delta transformation, it is possible for us to convert one shape into another. A pi shape can be converted into T shape because pi shape essentially is a delta connection. I suppose one can identify this is a delta connection. So this can, hence it can be converted to star. Okay, because it is very easy. It is very easy. If we have to determine y parameters, this pi shape is easy because if we can see in this particular y shape, in pi shape, if I have to determine y11, it is simply y11 is the sum of these two, ya plus yb. This is important. Ya plus yb. Whereas y21 is yb. This is minus yb. Okay, so these results can be directly used. Similarly here, y22 is yb plus yc, and your y12 is minus yb. We can make use of these results. But you should know, if I have to make use of these results, you should know what is ya, yb, yc. If at all you want to make use of these results. Otherwise, from first principle, it is simple enough. We have made use of first principle and we determined the two-port parameters, right? Two-port admittance parameters or short circuit parameters. And this completes the problem. All right, I suppose you have understood this. As far as this statement and its proof is concerned, maybe I'll make a video for this. Okay, so how is it we say when two networks are connected in parallel, the y parameters of the resultant network is the sum of the y parameters of the individual networks? How do we claim this? So we need to make the proof of this particular theorem. Okay, I'll try to take it up in the next video. And thanks for watching. If you have any difficulties, you can post. That will be taken up. Okay, thank you.